Have you ever thought what happens to the saved passwords in Chrome? I mean, all of us have used this feature, right? You just click save and passwords magically appear right when you need them. Well, what's actually going on is that Chrome saves your passwords in an encrypted form locally in a file called local data. And in today's video, I'm gonna show you how to write a script in C that will extract those files and unencrypt them. As I mentioned, passwords are saved in local data file along with corresponding URLs and emails. You can find the file under the directory you now see on the screen. I'm not gonna show it to you for obvious reasons, but you can pause the video and take a look for yourself. Now, the encryption algorithm used there is AES-256-GCM. Those of you who have watched one of my previous videos about ransomware development are already familiar with symmetric encryption, but if you are not, don't worry, I will explain everything as we go. As with every encryption, we need a key, and this case is no different. You can locate the so-called master key in the local state file under the user data folder. But obviously it's not stored as a plaintext. Firstly, our key is encrypted by DPAPI, or Data Protection Application Programming Interface, which is a feature in Windows that allows encryption and decryption of data using users' or machines' credentials. The encrypted key is then encoded with base 64 and stored in the file with encrypted key label. But enough theory, let me show you the code itself. So as always, we start with the main function. Now be sure to include all of those. I will of course tell you what those libraries are for, most of them at least. Okay, but first things first, what's not constant in all of the paths, because we can't directly hardcode the path to local data and the path to local state files. They differ. For each computer, this path is different because of the username, of course. All of those contains unique usernames, so you need to extract it first. And we do that with getEnv function. This is a part of Windows.h library, right? So getEnv, which is get environmental variable, and we are getting the value of environmental variable username. We are saving saving it to this char variable. Right. So we just check if it's not null, and if it's not null, we print it to the screen. Now, next thing, we build our paths. Password path is a path to local data, and encryption key path is a path to local state files. We do that by first declaring a buffer with max path length. You might already know that, but if you don't, 256 is the maximum path length in Windows by default. You can disable this limitation, but by default it's 256. So we are doing that, and with snprintf functions we are basically building those paths, and we save them to their corresponding buffers, to their corresponding variables. And then we of course print both of those to the screen. It's just for debugging purposes, of course. The actual malicious script wouldn't have those, and yeah, so that's just for debugging. Now, we want to, first things first, we want to extract the encryption key from the local state file. We do it with getEncryptionKey function. I will show you what this function does in a moment, and yeah, we are basically getting it and saving it to encryption key variable. So let's actually check out the getEncryptionKey function. It's here on top. And by the way, if you haven't watched my previous videos, in all of my codes there is this display error message function. It basically shows you, it prints you it takes the error code as input, and it prints you the text representation sort of this error code, because there is a list of error codes and corresponding messages to them. So when you just use the get last error, for example here, you could do it like this. Let's say %s and get last error. So if you do that, print function would print error unable to get username, and then it would print a number, and this number would be an error code, which you can then download and Google it and check what it is. But if you want to skip this Googling part, you can write this function that will translate the error code to the explanation of this error code directly on your screen, sort of. So yeah, it's very handy. It saves time. But yeah, let's go with get encryption key already. The only thing this function does is it looks for a string, for a specific string inside the text file. So as input, it takes encryption key path, and first thing we do, we open the file with fopen. We are using file variable. File structure, not a variable, file structure. This is a part of windows.h library again. And if the opening procedure succeeds, we are basically going through the text with fgets. So we are getting the buffer, which is max line length, and we are saving the first 1024 bytes of the text file into this buffer. We check if inside this buffer is this label. So if this string is present, quotation encrypted key quotation and colon. If this is present, then we proceed to the next inside the next if statement. So if this is not present, key start would be a null, and we would basically skip, go to the next rotation of this, to the next iteration of this while loop, and therefore we would check inside the next 1024. So if to summarize it, first 1024, if there is no encryption key string, we move to the next 1024, and so on until we find it, or until the file ends, basically. So yeah, so if we have our buffer, we are declaring this, not declaring, but we are updating this offset variable so that it starts, so that it it points to the address of the current, of the start of encrypted key, basically. Then we are moving to this address with fseek function. We allocate a buffer for our key, and if it succeeds, we get the next 1024 bytes. We get the next 1024 bytes, and we save it to this key buffer, right? So yeah. And if it all succeeds, we are basically closing the file and returning the key buffer. So just for you to be aware, this would, for example, look like this. We would have this encrypted key label. I'm talking about the key buffer. We'll have this encrypted key label. Then we'll have our encrypted key, and then we'll have some more stuff from this from the file. Because, of course, the encrypted key is shorter than 1024 bytes. I think, yeah, I'm for sure it's shorter than 1024 bytes. So we will catch even more, we'll retrieve even more, but don't worry about it, because in the main function, we are actually getting rid of the unnecessary stuff. As you can see, yes, we are saving the key to the encryption key variable. We are like double checking if there actually is this encrypted key, and we are moving the pointer to the start of the key, because the key starts just after this label, right? This label is not a part of a key, so we are moving the start of our string to the end of encrypted key. So we are basically skipping it, and then we are declaring the end of our string to the next to the next colon, sign. So we are basically cutting out the unnecessary label, and we are cutting out the unnecessary data at the end that we gathered from get encryption key. Now, if this succeeds, because we are of course have to do some checks. If it succeeds, we basically use string copy to copy the key itself to base64 key buffer, and we are printing into the screen. And now this base64 key holds the base64 encoded key. Yeah. Next thing is to base64 decode this key. So of course we do the dword decoded length, the variable that will hold the decoded length. By the way, as you may see, sometimes I'm using the standard variables, sometimes I'm using the Windows API variables. It might be sort of confusing, I know, but it's because some stuff is not directly connected to Windows.h library, and some stuff is directly connected. So when I'm working with with Microsoft's documentation, and they are using those like dword, because dword is just unsigned long. This is literally the same. I could have just typed here unsigned long, but the base64 decode function, for example, as I will show you in a second, uses a bunch of Windows API functions. So yeah, I just try to stick to the documentation, and yeah, I hope it's clear for you. Yeah, but if it's not, just tell me in the comments, then I will decide which one, or maybe you decide which one would you prefer to use. Do you want me to use the standard variables, or do you want me to use the Windows API specific ones? But yeah, enough talking. Let's go to base64 decode function, and let's see how it does its magic. As you can see, we're gonna use crypt string to binary A function to decode the data, and you may already see that we are using it twice. And again, if you have watched previous videos about encryption in them, I think it was the one with shellcode injection and one with ransomware for sure. So it's very common in WinAPI functions with WinCrypt functions, because yeah, that's very important. Before you use it, you have to include wincrypt.h and also include this line. Don't forget to do this. Without it, it won't work. Now, crypt string to binary A is used twice here because we need to figure out the length of the decrypted data. Now, basically how it works is that in our first run, we declare first parameter, which is the encoded key, second parameter input length, which is the length of encoded key. Crypt string to binary is a flag that specifies the format of the base64. I can show you that in the documentation we have a couple of possibilities. We have crypt string base64, this one we are using, which is base64 without headers. But there are base64 encoded data that do have headers. So basically, just before the data, you have the begin header, and after the data, you have the end header. And if that's the case, you would go with this value here. But we don't need that. Now here you want to pass null because, as you can see, this parameter is called PB binary, which is a pointer to a buffer that receives the return sequence of bytes. If this parameter is null, the function calculates the length of the buffer needed to return the size in bytes of required memory in a dword pointed to by PCB binary, which is next argument. So we we want to save this decrypted key somewhere, okay, not decrypted, but without encoding somewhere, but we don't know the size of the this buffer. So we need to we figure it out by passing null here and by passing output length here. So basically this d word after this function runs, this d word will hold the length of decoded key. The last two parameters are irrelevant for us, so I won't spend time discussing them. Now, when we know the output length, we can allocate enough memory so that our decoded data can be stored somewhere. So this is just basic malloc. And again, we are using the same function, but with decoded data here instead of null. And we are returning decoded data. So I think this is pretty clear. So let me move to the next thing, which is print hex. Okay, like print hex is just, again, for debugging purposes. This is a function that prints the decoded key in hexadecimal form. So you can do this, but you don't have to. Now, decrypt data. This is one of the most important, if not the most important function in this code, because this thing removes DPAPI encryption from the key. And here, as you can see, I experimented with this structure, which is called data blob, which comes very handy. And it's very simple. It has two fields, one which is called PB data, which is a pointer to the start, pointer to the address of the first byte of your data, and CB data, which is the length or the size, if you will, of your data. So this is the decrypt data is of a type of data blob, so it will be returning a data blob. We pass encrypted data that we got from our base 64 and encrypted data length. This actually is kind of misleading. This should be decrypted, not no. Okay, okay, okay. Just don't listen to the last 30 seconds. Sure. Okay, where were we? Yeah, here. As you can see, encrypted blob.cb data, we pass encrypted data length. And to pb data, we pass the encrypted data itself. Okay, so once we do that, we allocate memory for the decoded data, which is of length, of size encrypted data length. And then we need to subtract, we need to cut the prefix from the decoded string, because I didn't tell you, but when you decode, when you basically, after this function, you will have the key, right? The encrypted key, but it will have a prefix. Basically, there will be a DPAPI, just 5 letters before the actual key. So we need to cut it off by moving the pointer by 5 bytes and subtracting 5 from the overall length. Yeah, so this way we won't have the prefix anymore, and we can use crypt unprotect data function that will remove the, or that will basically and decrypt the key. And we pass here encrypted blob, the encrypted blob, and decrypted blob. So this function saves the decrypted key to the blob, which is of course of type data blob, and it returns it. And this way, in our main function, we have what's called a master key, which holds, as you remember, the key and its length. And we print it to the screen in hexadecimal format and in non-hexadecimal format. Now, as we have the key to decrypt the passwords, so last thing that we need to do is to actually decrypt them. So let me show you how we do that. There's one more thing that you need to know. Basically, the local data file is actually an SQL database file, sort of. And we will use SQL queries to extract the URL, email, or username, it depends, and the password value. We do that with SQL library. To use it, you actually need to include SQL, SQL3.c and SQL3.h files. Link to both of those are in the description. Just make sure you have them in the same directory as your main.c file or stealer.c file in my case, or whatever you name your project. Yeah. So first we initialize the structure of type SQL3. And also, by the way, remember to include the SQLite.3.h file here in those quotation signs. Yeah. Okay. Where were we? We open our database. We pass here a path to the file and the and we get the basically the structure, our DB. Then we'll be able to communicate with the database by using the structure. If it succeeds, we get this print that opened SQL database successfully, and we want to execute our query. So we save a query in this variable as a string, which is select origin URL, username value, and password value. So those are fields that we want to select from logins. This is the table. And if it succeeds, we will have a print that executed SQL query successfully. All right. Now, and this query is saved here in this SQLite3 stempty structure. I don't really want to focus on how this SQLite library works. I can link you a documentation in the description of this video if you want to go through the details. But yeah, once you do that, we enter a while loop. That will go through all the rows that we extracted, and we are saving the first. Because as you remember, here first value that we were extracting was the origin URL. So the first the first, you need to pass basically 0, 1, 2, which is 0, 1, 2, just like this. So origin URL will be of index 0, username value will be of index 1, and the password blob will be of index 2, but here is the difference, because I had a pain with this. We need to extract it not by using SQL3 column text, but SQL3 column blob. And also, we need to extract the password size by SQL column bytes. The encrypted password has has three things inside the whole. Like in an encrypted format, it has the prefix, which is v10, just v10, which you have to remove. Every password has it. I don't know what is it for, to be honest, but it's there, and it's not a part of the password itself. It's just a part of this encrypted string, so you just need to remove it. And the next 12 bytes is the IV used while encrypting the password. So we also need to remove it, but we also need to save it because it will be necessary for decryption. And as you can see, we are copying to the IV buffer declared here. The first, okay, not the first. We are moving by 3, so we are skipping the IV part, 1, 2, 3, v10. We are skipping the IV part, and the next 12 bytes, which is the IV, we are copying to the IV buffer. If it succeeds, it will print the IV in hexadecimal form. Now, same goes with password. We are allocating the size, because we don't know the size of a password. The IV is always 12 bytes, always. But the password depends on the password. So we are initializing a buffer of password size, and password size is this, which is the size of the whole thing. So we are initializing a buffer of a password size minus 14, which is minus IV minus prefix plus 1. So we can get a null byte here. Because remember, every string value, every string in C has to be ended with a null byte. And yeah, we are copying the yes, we are copying the password to the password buffer. All right, and then we are printing it to the screen again in hexadecimal form. I want to print all of this in hexadecimal because these values, when they are encrypted, they are not UTF-8 characters, so it looks like a mess. And yeah, I don't know. I just prefer to see it as hexadecimal. But again, you can print it as you wish. It doesn't really matter. And the last thing, to be honest, the actual last thing is the decrypt payload function, which takes the password size minus 15, so minus prefix and minus IV. It takes the masterkey.pb data, which is our key. It takes IV, and it saves decrypted password back to the password buffer. So let me show you this last function, decrypted payload. It's somewhere here on top. Yeah, right here. So as you can see, it's a very small function, like what, 1, 2, 3, 4, 5, 6 lines, and like 2 lines that actually are functioning, like for real. Okay, we are using libsodium library here to perform the decryption. And to use libsodium library in your project, and which is the most important, to make it be inside the executable, because you want to, when you are executing this script on like a computer that doesn't have libsodium installed, you want your program to carry the library with it. And to do that in Visual Studio, we do what's called a static linking. I will give you a link to the libsodium library in the description, so you can download the pre-compile libsodium.lib file. It looks like this, libsodium.lib. And to link it, to perform the static linking, to go to project, Chrome password stealer, which is my name of my project, properties. You go to First, you go to this C and general. Here you need to pass the directory of your header files, which is additional include directories, right? A path to the header files, which is here. When you go to libsodium, include, and you pass here this path. Next thing, go to preprocessor. And preprocessor definitions, type here sodium underscore static. And last one in linker and general, okay, not the last one again, not the last one. Additional library directories. Here you pass the directory of the libsodium.lib file, which is x64, release, 140, static, so this path. And in the input, you pass the libsodium.lib, which is name of the library, of the file. All right, so once you do that, you are ready to go. As you see, the input of decrypt payload function is, okay, let me actually go to the bottom, password, wait, I already said that. Why am I repeating myself? Okay, never mind. So yeah, crypt AEAD AES 256 GCM decrypt. It takes a lot of parameters. First one is the buffer, the location of the decrypted key. So this function will save the decrypted key here. Here is here we specify the variable that will hold the decrypted key length. Here we pass null, ciphertext, which is our encrypted, key, ciphertext length, which is encrypted, okay, not key, password, encrypted password, which is encrypted password length. You pass null here, 0, 0, don't bother. Almost, okay, not last. IV parameter, this IV, you just pass the IV that we extracted from the password earlier. And the last parameter is key, which is the master key, the DPAPI encrypted key that we got from this decrypt key data function. All right, so once you do it all, the decrypt payload function will save your decrypted password in the password variable, and then decrypted password is printed to the screen. So let me show you how this works. You won't see much because I will have to blur most of it. But yeah, here it is. The output of our script. I won't scroll down, so I don't wanna waste more time blurring stuff. But as you can see, we have the decrypted password here. We have the password in the hexadecimal format, unencrypted. We have all of those data that we were printing to the screen, and also a username that corresponds to the password, and the URL where this, the URL that URL to where these credentials belong, basically. So yeah, that's how it works. This simple. Okay, but some of you may say that you are just printing those files, you aren't really stealing them. And yeah, you are right if you said so. We are just showing that we can decrypt the passwords. We are not sending them anyway. And that's the thing that I want you to do. And this is the first time I'm doing something like this. I want this video to be a sort of experiment because I want to add some interaction so that you're not only staring on the screen and listening to how I explain the code. I want you to modify this code, to do your research and come up with a way of extracting these passwords. As for the research, what I would do is to just Google how to send data over HTTP in C. Just try to Google this phrase and see what comes up. And then paste your code, link to the GitHub, for example, or in some way share your code in the comments so that we can see it, we can check it out. Yeah, basically, let's see who can come up with the best, the most elegant, the quietest, because that's what's important in data exfiltration, way to perform the actual theft of the passwords. And that's the end of this video. If you enjoyed it, please leave a thumbs up and leave a comment with your code modification. So one more time, I encourage you to take your part in this experiment. People are learning by doing stuff, not by listening to stuff. So keep that in mind. And yeah, see you soon.